Oh hey, welcome back to the channel. Today I thought I would make a video going over the importance of using computer-generated noise like simplex or Perlin noise to sort of give your projects a level of randomness that is achieved in nature. It's a very common methodology to achieve that. And so I thought I would break it down using Grasshopper, starting with like very simple one-dimensional noise, as you'll see here, and moving into slightly more complexity. I put the chapters down below so you can fast forward if you don't care about the one-dimensional and 2D aspects of it. You can skip towards the end. Yeah, let's get into it. All right, here we are in a Grasshopper, and as you can see on the left, I've created this sort of very one-dimensional noise, which we're starting out with. And for the one-dimensional and two-dimensional noise, we're both going to be using just Graph just to keep it really simple. The way you can find this is going into Graph and then right-clicking, going to Graph Types, and there's a lot of them there. But the only one which is actually a noise is the Perlin. So you're going to see this Perlin noise. And you can go ahead and drag and manipulate this, and it's pretty nice because it's going to output a lot of different values, and you can have a very fine control about the amount of noise and whatnot. Anyway, so I'm using this graph mapper to achieve this noise. This is quite simply just a range of numbers that is going directly into the X output, and then that same range is going into the graph mapper and then being remapped in order for me to be able to control that noise value externally without jumping inside this component to the X and Y values here. So I'm externally remapping those to control it, and then it's just constructing those points, and then I'm simply putting that into a polyline. And so this is really quite simple. I'm not going to spend too much time on the one-dimensional noise. I just think that's fundamental for you to understand eventually the three-dimensional noise and four-dimensional noise. Okay, so let's move on to two-dimensional noise. Let me turn this off. Let's go to the two-dimensional noise. So, and you're going to quickly see the problem with this one as well. So what I have here is a surface, a NURB surface, that I am creating simply by creating two ranges, each with 20 values. As you can see right here, 20 values. And I'm using the cross-reference component, which can be found here in the set. I'm doing Control Alt. That's how you can do that display, which is pretty convenient. And then what is happening? So in this cross-reference just essentially gives you two lists. So I'm giving you two sets of numbers between 0 and 10. And the first one gives you all 440 of those actual numbers needed. And the other one gives you 440 but corresponding. So it's, and what this does is it allows you to be able to actually create a grid. You can also do this a million other ways by simply grafting one side of, by grafting when you create the X and the Y, you can just graft also one input into the X and Y here, but I just did it this way just because I like to explore new things. Anyways, then what's happening is that then both of those inputs are going into a graph mapper and each controlling a different sign value. And what you're going to realize is that this sign here is controlling this X variation, this X, and this sign here is controlling the Y. And then simply I'm multiplying them together and remapping those numbers. So once again, I can control the Z height, and this is forming the X values for my grid. And you can also, of course, export those as into a sort of Delany mesh, which you can then go ahead and Catmull Clark and subdivide for smoothness. Let's give that to a level of 2, hide this, and all of a sudden you can see it. But the limitation, I thought I'd show you this because the limitation of achieving trying to achieve sort of this pseudo three-dimensional randomness by cross-referencing two different sets of elements of noise, is that what you're doing is you're creating one face of noise on the front here. Let's go to the front or left. So you're setting one set of noise on this side and then referencing it to the other side. So if I go to front now, and you're referencing it to this set of noise here, and you'd think that this would go ahead and make a this would make, you know, a oh my god, why did the seaplane change that? You just type in seaplane world and then top to go back to your original. Anyways, but I'm just showing you the problem of trying to cross-reference two planes of noise to create one three-dimensional plane of noise. That doesn't quite work because you're seeing a consistency, and you can still see the repetition of that noise across the surface. So what this leads us to is this 4D noise, which you can download at this link here, and I'll put it in the description. This is a great plugin which brings us two components, which you'll see here: simplex noise, and also Perlin noise. So these are the two components of this plugin, and what it's going to ask for. Both of them have the exact same inputs and output. It's going to ask for 3D points as an input, T, which is time, which is sort of where it gets that fourth dimension, right? It could be three-dimensional, but the second you add time, it adds that fourth dimension and allows for variation in your noise. And then also the S on both of them is scale. I'm going to do two exercises. Let's create our first example, which is going to be a cloud of points that we're going to manipulate the radius on spheres that are assigned to those points. So you're going to see these sort of cloud of spheres that are manipulated by the noise, and we can see how we can adjust that also using the T scale. So let's begin by just creating a box, and let's just create a center box. And that's ridiculously small, so let's scale that up, just 10, 10, 10, 10, 10, 10. Then we're going to need a series of points, so a good way to do that is just populate 3D, super easy. Let's leave 100 points for now in case I assign something wrong, and so it doesn't explode my computer, which would be terrible. And I do that quite often. I'm experienced in that. So now we're going to need to create a series of spheres, and we can first keep the radius the same, and then we'll see what happens. So let's use an icosahedron, which is from the Weaverbirds component. You can click here, and you can see that it's within the Weaverbird. So I highly recommend the Weaverbird plugin. And now if you can see, if we simply connect those points to the planes, we can assign those. But first, let me actually explain why I use this rather than a mesh sphere, for example. Sphere. So let's show a mesh sphere. So if I use a mesh sphere, what you're going to notice is that the topology, although it's clean, it actually has a lot more faces near the top, and they're much smaller faces, and they're actually triangles. And then if at the middle you get a lot of big faces, and there's less of them, and then or less concentrated, and then at the bottom you would get the same top condition where you have a lot of smaller, more concentrated. And this, when you use displacement, which we're going to use because we're using noise, causes a lot of problems because you're going to get more displacement at the top with all those vertices up there and less at the sides. So what I prefer is to use this icosahedron, because when you subdivide it, which I'll do right here, cat small Clark. Let's set that just to 2 for now. We can increase this later. When I subdivide it, you get an even distribution of faces at the top and at the bottom. So later when you're displacing it, it's going to be a much more even distribution of displacement. So that's sort of a nice tip to remember. And I can already see these are going to be way too big. So just quickly, I'm just going to lower that to like 0.5 or 0.6. And now with these, we can simply plug in, all it's asking for is a plane, which we can just use or populate as that plane. Okay, so now we can see we already have a grid of these things, and I'm gonna hide the non-subdivided so we can just have the nice clean subdivided spheres, actual spheres. So what we're going to need to do is actually manipulate this radius, and I'm going to do that by dropping in a simplex noise, and I can show you the difference also between simplex and Perlin in terms of actually 3D. They're both created, here I'll bring in, they're both created by the same guy. I think its name is Ken Perlin, and they both serve their purpose, and I don't really have a preference. I think some people do have preferences with this sort of thing, but to be honest, you could use either one and you won't see radical differences. I also overlaid a visual that I made showing you what they both look like, so you can see there's a difference, but choose them as you will and just interchange them. I think I prefer simplex, but I don't know why. I couldn't tell you why. Okay, so let's quickly, all we have to do is input those points. Then we have time, which I'll create a slider. 0.00, and it'll go up to 1. So we're gonna have a slider, and then we can have scale, and I'll adjust that later. So let's see what this is outputting for us. As you can see, it's outputting a series of numbers between, and let's check the bounds so we can actually see. The bounds is telling us that it's outputting numbers between 0.6 and 0.74. So when I don't really want my radius to be a negative number, and I don't really want it to end at 0.74. So I'm going to do what I always do and remap those numbers. We're going to put all those numbers into the values. The S, which is the source as we know it, is going to be this bounds. And then we're going to create the new source domain with the construct domain, which is my actual least favorite component because I feel like I have to type in construct domain or else I will not get it. And I know I can go and change the shortcuts. I'm just too lazy to. 0.5, 0.5. So now what we can see is that all those results are between 0.5 and 0.5. And then as I adjust it, we can see we can start to get a lot of control about the sizing of that. So now let's make sure our data trees line up before we plug this in because it's going to explode. So we just want to assign one of these values to one of the radiuses here. Let's see if it works. And it does, because we're supplying the exact same amount of values as we're supplying points to each icosahedron. And now we can sort of fine tune this in C. Let's actually increase the at the risk of exploding everything. Let's increase this. Actually, you know what? Let's be ballsy. Okay, so we have this now, and we can see that. I'll show you what the Perlin noise does in a second. But what I want to show you first is the T. So I want to go over this T and the scale. So the T is time, which is the 4D aspect, 4D aspect of this noise plugin. And you can see this has a really nice effect in how powerful this could be, especially if you're animating or need to test a bunch of variations of noise moving across time or space. What scale does is it changes sort of the density, and this is something you can see when you do it on a flat plane. You can see it incredibly clearly, and maybe I'll put an image up on the screen of changing the scale, and you can see if I go to a larger number, it also seems to increase the density and the repetition. And I find it generally you want to use small values because larger, it doesn't seem to have as nice of an effect. So I'll just leave it at that. That's not the most interesting one to manipulate. Anyway, so this is simplex, and let's just quickly convert this into a Perlin. We can just plug those same values in, and then just Control Shift and just plug all of these guys into here. And you can see now the scaling and time difference on this Perlin noise, which is quite beautiful actually. So maybe I changed my mind, and now I like Perlin more than simplex. I'm a very tough man to please. Okay, yeah. So that's quickly our first example of in 3D space. Now let's move on to our second example. Okay, now we're at the point where I think everyone skipped to. So we're going to use a 4D noise to displace a mesh sphere into sort of this undulating planet-like organism. If you fast forwarded, then you do not understand why I like to use this Weaverbird icosahedron, which I explained in the beginning of the previous exercise. So just go check that out. But anyways, basically it's just so when I subdivide using Camel-Clark, we get an even distribution of faces, which you will not if you just use a traditional mesh sphere. So we have this, so what we're going to do is we're going to be displacing these mesh faces. And this can simply be done. Let's just put it down a mesh container. Okay, so we're going to take this mesh and just displace it. So we're going to need to deconstruct this mesh, which is right here. Deconstruct mesh to its vertices, faces. And so we're going to take those, what we're going to be using is we're basically going to be using these vertices to be supplied as the points to feed into our simplex noise. And then we're going to be so then we're going to displace those based on the normal, which you can see is also supplied by this deconstruct mesh component. So what we're going to be doing is applying mesh. So we're going to put these vertices into this point. And we can again supply a timer to the simplex noise. And then what this is going to output is another value. So we're going to have to remap, similar to last time. And then we're going to be moving those values. So we're going to be moving these same points. And we could say, so if I move it by just the normal, it's moving it by the normal of each point, and the amplitude, the base amplitude is 1. So let's change the amplitude. So we're going to take the vector that is normal, because normal is a vector, and now we can manipulate that. So here we have the base, it's set as 1. So this 1 that's input in here, the amplitude, is going to be what we're supplying with this simplex noise. So similar to last time, we can see that simplex noise is going to be exporting a number between, bounds. We're seeing that it's exporting a number between negative 0.9 and 0.899. So we want to remap these again. Remap. This will be our new domain. We can delete this. We're going to have to construct domain again. Construct domain. Let's see if I can get it right. Construct domain. Perfect. Construct domain. And we're going to go between 0.00 and here, let's do the little shortcut. Where is that? There, and 1. Now we're going to create that, and then so we're going to displace those, and we're going to supply these as the amplitudes for that vector. And then as we increase, we're going to be able to see we're starting to apply some level of noise, which is displacing those points. But we need to reconstruct the mesh. So because we've deconstructed it, now we can reconstruct. Construct mesh, which is going to ask for vertices, faces. Luckily, the deconstruct gives us those faces and actually the vertices. So here's the faces, and then we have to supply the vertices. Actually, I'm going to put that down here. So this is all the displacement down here. And then this is the reconstruction of the mesh. And let's just hide these guys. And now we can see we have a mesh that has faces that if I now adjust the t-scale, the time, you can see we're starting to get something. Let's actually increase the values of this. Let's just put it at 5. I can really pump that out. And this is kind of ugly right now, so I'm just gonna, again, Catmull Clark, which is a subdivision process. I'm just gonna subdivide it down. I guess we can do 2. And then hide the rest of this stuff so we can just focus on the blob. Okay, so we have now a blob that can move. And it's pretty interesting, actually. The one thing I do want to do is actually preview and show you how to achieve colors based on the depth of this. Oh yeah, we can also, by the way, we can also change the scale of these of this noise from very soft to a little bit more hectic. Let's go somewhere in the middle. And also, of course, you can put in Perlin noise. And just substitute these guys here. And you can play with this as you want. Just gonna leave that there. Bring in those vertices here. And then we can just Control-Shift, hold down both these guys and put it into there. And it is gonna be a bit different, so you might have to play with it, but you can change the scale and also the time. Okay, anyway, so we're now using Perlin noise, which I declared before was my favorite. And it reinforces that. Okay, so let's actually see here, we actually have colors that we can import into the mesh. So let's use the depth that we're getting from the noise. So let's actually take the noise and remap that to assign it to a color. And we can do this using the gradient and again, remap. So here we can see we have a color gradient. And let's just find one that's, if you right click, you can go to presets and find one that's kind of sexy. I've always used the black and white because I'm basic. So let's do that. And what we're going to see here is it's similar to remap. It has a lower limit, which is automatically set to 0, and a higher limit, which is set to 1, which is conveniently the base output of remap. I'm not going to want to I could reuse this one, but what you're going to see is this is not between 0 and 1. So I'm actually just going to take another Perlin noise, and you're going to see that I can again take this bounds, go to here, and now we're going to have, and because this target is already automatically set to 0 and 1, now I can remap this into here, and it's going to give us a series of values on this that will contribute to constructing that mesh. So now when I plug this in here, you can see we're getting black dark values at where there's the most amount of noise displacement and white values where it's not. And we can kind of go in and crush this down, make it a little bit more extreme. And of course we can play with this a lot. And let's see what that starts to look like. You could of course extend this timer. There's a million variables to play with. But it's pretty interesting to be able to go back and change these things. You could also go in and of course change these Perlins with by overlaying different layers of Perlin. So you can like multiply Perlin by Perlin and see what happens and sort of that method. Actually, I think I will do that. One thing I did discover was it's kind of interesting when you take now the output of this mesh, which is this guy, and apply a second layer of Perlin to that. So I'm just going to quickly deconstruct this mesh. I'm just going to quickly repeat constructing the mesh. I'm going to copy and paste this Perlin, 2 more of these guys, bounds, remap, construct domain. This is probably a terrible way of doing it because it gets real confusing when you just copy and paste things over. But essentially, I'm just going to apply that second layer and see if we get an interesting result. So once again, deconstruct the vertices into this second new purlin. Then we're going to also bring those vertices to the points that are going to be moved. And then those normals are the new amplitude, because we have to update the normals or else it's going to be, it's not quite going to work. Then these mesh are going into the new vertices. We could just use these new faces to create something. And now let's hide our previous. We can see we have a very interesting result. And let's Catmull Clark again. Just subdivide it one more time and see what result we're getting. I mean, it's pretty bulbous, pretty interesting. Let's, maybe I should preview it with color. We can, of course, change the second layer of modification. And actually what I found is you could do this, which is let's actually bring in, let's just do this as a negative value. And you can actually get internal ridging. It's kind of hard to see with red, so actually let's bring in a second gradient. And we're gonna do the same thing so I can see better. We're gonna remap those new the new noise values. I could bring in the colors from the original one and recolor it, but I think it's just a little bit nicer to just to use the new one. So we're gonna insert that bounds again, and it's gonna automatically set to 0 to 1. Then we can put this into here, then recolorize our new mesh based on that. And then let's also crush these guys a little bit. Get a little bit more contrast in there. So one of the things that I do know is that now we have 2 time scales. So, which means I can manipulate both of these, and it's not quite what I want. I'd rather prefer to have 1 time scale, which I'm actually gonna isolate. So I'm just gonna plug this time scale into the other one and delete the second one. But I also don't want them both noise to start out at the exact same value for both of these components, the first purlin noise and the second purlin noise. So I'm actually going to right click on here, go to expression, and just go X, and let's just say plus, I don't know, 5. So now it's going to offset this second purlin T value by 5 while still maintaining that one timer. Let's actually also bring this up to like at least 2. We can see, so we can really start to see the depth, and you can also control. Of course, you can go in and change these things. What I do want to get this to be a better negative. You can what happens if I actually just put this into there? Interesting. And then let's maybe reduce it a little bit. Or increase it. Well, it kind of collapses on itself. Maybe just a little bit. And also we can change the scale of this guy. So maybe it's much denser. The second noise, it's much denser. And then maybe we can afford to increase, decrease. Let's see. Of course, you're going to end up playing with these sliders a lot. So anyways, I think I'm going to end it there. Let's see if we can get this to look real sexy. If you have the human component, you can do custom preview materials. What this will do is you can just plug that in here and then turn this off. And now you have a really nice looking object with one slider that you can control the T values for and get some really interesting results. Anyways, okay, I think I'm going to leave that there. That's kind of what I wanted to cover today using noise. Please be sure to like and subscribe to my channel if you like my content. I hope you enjoy. Please also just let me know what you can create with this sort of thing. you can supplement anything into here. You could, I mean, there's no reason you have to start with a sphere. You could start with a base plane and just create ripples. You could do any sort of thing. Anyways, I hope you kind of enhances your understanding of it. All the links will be in the description. Yeah, thanks a lot.